This is video 3 in the lecture on BMS safety. After one slide to broadly discuss safety analysis tools, this video will focus on fault tree analysis, or FTA. There are 3 safety analysis tools that I'd like to mention. First, engineering intuition underlies how well you can use other tools. If you've done an analysis and something feels funny, think harder about how to fit that feeling into your rigorous tool. Second, fault tree analysis, or FTA, results in a tree that looks like this. At the top, we have the event that we want to prevent. And then we run a top-down analysis to find all the root causes. We'll go into details in the following slides. The third safety analysis tool that I'll discuss is Failure Modes and Effects Analysis, or FMEA. FMEA produces a table that looks roughly like this. In addition to listing failures, FMEA assigns numerical ratings to the severity to each failure, to the estimated likelihood of occurrence, and to the ability to detect the failure. We'll discuss more later. Let's go deeper into my favorite safety analysis tool, fault trees. A fault tree is a top-down analysis with the top event being the failure that we're trying to prevent. Then we build a tree of events whose relationships are described by gates. In this example, we see an AND gate. The events at the bottom of the tree are the primary events, or in other words, the root causes that could lead to the top event. And what's the goal of an FTA? An FTA shows us where mitigations are needed. For example, if we're concerned about a person putting their finger in a powered socket and getting an electric shock, we might implement training to prevent people putting their fingers in sockets. Or we might redesign the socket to block finger access. There are standard symbols used to represent FTA events. A basic or primary event is represented by a circle. A rectangle can have either of 2 meanings. It is used for the top event and also intermediate events or states. In a bit, we'll see an example of what that means. Diamonds represent undeveloped events. And again, an upcoming example will clarify what that means. These 3 are, in my opinion, enough to do a decent analysis. You may see other symbols in use or in more detailed tutorials, but we won't go into them in this introductory overview. The relationships between events are represented by gates. You may have seen these in a class on logic or digital design. An OR gate means that the output event occurs if any input event occurs. An AND gate means that the output event occurs only if all the input events occur. And a NOT gate means that the output event occurs if the input does not occur. In my opinion, these suffice for a decent analysis, though a good number of other gates are used, and in some cases, multiple different symbol styles are used to represent a single logical concept. Before starting any rigorous analysis, it's critical to have a clear understanding of the design across your team. And there's nothing like a system diagram to ensure everyone envisions the same thing. This drawing is a good start. Better yet, you would include specifics like component values and connector part numbers and cell capacities and so on. Let's do an example FTA relevant to battery management. We want to prevent cell overvoltage, since overvoltaging a cell can damage the cell and possibly even cause thermal runaway. Cell overvoltage is our top event then, and represented with a rectangle. Think about what can cause an overvoltage event. There are multiple ways to express the same logical concept, so your answer may differ from mine. A cell overvoltage occurs when contactors are closed and the charger is charging the battery, although some cell is above 4.2 volts. The top event is represented by a rectangle. Diamonds represent undeveloped events. An undeveloped event is a branch that we can explore further. For example, multiple root causes could result in the system failing to stop charging at top of charge. So, let's go deeper. Since we are developing the event into its dependencies, we change the symbol from a diamond to a rectangle to represent an intermediate state or event. The system fails to stop charging if either the BMS makes a bad decision and requests or allows charging when some cell is above 4.2 volts, or the charger misbehaves and fails to stop the charge current upon request, which we might say is an actuator fault. We can leave the description charger charging with V cell greater than 4.2 volts. This is optional, but nice for readability. Or we can omit that description if the outcome would be obvious to anyone reading the fault tree. Use your judgment. Let's develop the bad decision fault. I'll keep the intermediate state because it improves readability. Readability helps reduce mistakes because a second engineer can more easily check and build on the thought process of the first engineer. I've actually been in the situation where I made a design decision, then left the company, and later learned that my manager redesigned that subcircuit and experienced the very problem that my design intentionally avoided. Had I clearly noted my reasoning on the schematic, I would have saved him time. First, let's change the diamond representing an undeveloped state into a rectangle representing an intermediate state. Then, let's consider what can lead to this scenario. Maybe a sense wire broke and we're measuring nonsense. Maybe a pin on the sensing chip lifted up from the circuit board, again, leading to measurement nonsense. Maybe we have a microcontroller fault. And in a complete analysis, you'd have even more causes. Notice some judgment involved in listing these events. For example, the broken sense wire and lifted chip pin are similar. Both are ways in which the voltage sensor disconnects from the cell. Whether we list them as two events, like I've done here, or combine them into a single event, is a matter of engineering judgment. Similarly, the microcontroller fault could be an undeveloped event, and we could go on to list primary causes such as ESD damage and a short on the power pin and latent failures and so on. Or we could just leave it as a chip fault and change the symbol to a circle and consider it a primary event. We didn't quite finish this fault tree, but we have enough that I can show you how to use it. For single-point fault detection, we need a diagnostic or mitigation for every fault that could cause the failure we're trying to prevent. So, let's design a diagnostic: broken wire detection. Let's look at the related subcomponents. Perhaps we have a cell or maybe a group of cells whose voltage we're sensing. Then we have a connection, say a weld to a wire, to another weld to a bus bar, to another wire to a connector, to a printed circuit board, and a trace on the PCB brings the signal to a pin on a voltage measurement chip. Now imagine the sense wire breaks. Our measurement system is no longer connected to the cell. How can we diagnose this failure? Consider the circuit. The fault in the picture on the right corresponds to a break in the circuit on the left. For convenience, assume the cells are at 4 volts each. Our measurement chip will see the correct voltages for 2 of the 3 sense connections and an undefined voltage at the third. How can we perturb the system to a state where we can tell for sure which of the sense pins are correctly connected to cells and which is disconnected? One possibility is that the BMS chip can implement a small current source which can be turned on at carefully selected times as a diagnostic tool. If a cell is correctly connected, the measured voltage will barely budge because the diagnostic current is tiny. If the cell is disconnected, however, the voltage will collapse and the corresponding channel will measure 0 volts. We can detect a sense wire disconnect. Let's take a look at the next fault, a lifted BMS chip pin. The circuit representation of the fault looks identical to the broken wire situation. With this realization, we can simplify our fault tree to merge these 2 faults into one category. This both simplifies and improves our fault tree in that it now captures failures anywhere along the path from the cell to the measurement circuit. And in this manner, we would go through the entire fault tree to build undeveloped events down into root causes, and then to ensure that every primary event has an associated diagnostic or other mitigation. To summarize, fault trees are a top-down tool wherein we start with some concerning top event that we wish to avoid and use an FTA to identify all single-point faults that could lead to that concerning top event. Fault trees are useful because they facilitate development of mitigations to all relevant faults. They are a good tool for guiding design and simple enough for design engineers to use in addition to their other responsibilities. They require a good understanding of the system, so are best done by an interdisciplinary team. And lastly, I'll note that fault trees don't reflect the severity nor probability of the events that they describe. That's not a bad thing, as you'll see with the next tool that we discuss, including that additional information impacts the readability of the analysis. This is the end of video 3 in the lecture on BMS safety. Please continue the lecture with video 4.